Yeah, it's just after 2 o'clock, and so yeah, it's a pleasure to welcome this week to our Applied and Computational Maths seminar, Chris Ness from the University of Edinburgh. Chris kind of flip-flopped back and forth between Cambridge and Edinburgh, doing his undergraduate in Cambridge and PhD in Edinburgh, postdoc in Cambridge, and now he's a Royal Society of Engineering, is it? Royal Academy of Engineering fellow on a 5-year fellowship, isn't it? At Edinburgh. And so, yeah, so Chris is working in the engineering department there, but also has strong ties with the physics department. And yeah, I think a lot of the methods he's using, and, formulated in these traditional continuum mechanics and high quality mathematics as well. So pleasure to hear about Chris's believed principles in suspension flow today.
Okay, thank you very much, Tom, for the introduction and for the invitation and for hosting me so generously the last couple of days. I think calling a talk Unifying Principles is a bit much. So, and what I'm going to talk about isn't just my own work, but I spent the kind of initial part of the pandemic writing a review paper, which I'll mention at the end. And in doing so, I kind of gathered together a lot of ideas from the literature, which are kind of well established. So, I'm going to present those to you today. So it's more hopefully something that is kind of pedagogical for you, sprinkled with a little bit of my own contributions. So I'm not suggesting that I have unified this enormously complicated field, but the community as a whole has established some general principles in the last few years that are both interesting and useful, I suppose. So that's what I'm planning to tell you about today. So because I'm from Edinburgh, this is what you think my research group looks like. Well, I can tell you it doesn't, although that's me. So some of my research group looks like this. But the others are just normal, non-bagpipe playing PhD students, like I assume you are. If not, you can tell me. That would be interesting. So yeah, I have a group of 3 PhD students, postdoc who's just going to start next month, and I've had a series of master's students. So I'm kind of not going to mention any specific work that they've done, but just thank them as a whole for the discussions and ideas and things that we've exchanged. So I'm going to talk about suspensions, which there are many examples of that are practical and relevant to understanding the natural world, understanding industrial processes, and understanding consumer products, things around the house, things which are manufactured and things which we use daily, like chocolate or toothpaste, the kind of the opposites of each other in terms of your mental health. So I'm not interested specifically in one of these examples, but rather asking general questions that apply to all of them. So you can think in all these contexts, we might want to know what's the viscosity of this material. Does it have a yield stress? If so, how can we understand the yield stress? If we want to put this in a pipe, I'm a chemical engineer, so basically everything I think about is what happens if you put it in a pipe. So if we put these in a pipe, how big a pump do we need? How fast will it move? And so on. And then when it leaves the pipe, what will its surface look like? These are all very broad questions that have elements of fluid mechanics, solid mechanics, and so on. But we can ask these of all these materials and expect that there might be some common principles in how we answer them. And like I said, the applications of this are quite broad. So as far as I'm concerned, these 3 examples are unified by the fact that they all are just some solid particles, which is the gray circles, liquid, which is the blue kind of interstitial material, and there's some flow, which is the arrows there, which are showing that there's a velocity gradient. So from now on, I'm going to kind of omit these 3 things and just focus on this as a kind of model system in which that we might understand the flow properties of mixtures of solids and liquids. So just before I completely go into neglecting all complexity, this is what these things look like in real life. So these are silica spheres, which are around about 1 micron. These are the type of model systems that people use to study the flow properties of suspensions. So you can see it's dense, which really means that the volume occupied by the solid particles and the volume occupied by the liquid are roughly equal, or the same order. So it's 50-50 solids and liquid, roughly, something like that. A slightly more complicated case, if you actually look at a real suspension, generally it might look like this. So you have aggregates, particles with a complex shape and broad size distribution. Even as far as suspensions go, the one on the right is very idealized in that the particles are the sizes all the same order of magnitude at least, and they're kind of their aspect ratio is not very high, so they're kind of distorted spheres in some sense. These are the types of materials that are of interest, but I'm going to focus on the one on the left, which is a bit there's fewer parameters, I suppose. So why, before kind of going into how we describe these things, it's useful to kind of remind ourselves of why it's not easy to do this. So I've highlighted some challenges here, which make mathematical modeling or computational modeling of these systems difficult. And you can express these ideas in different ways, but this is how I like to do it. So these systems are out of equilibrium. And what that means is the particles are not molecules or atoms like they would be in water or in a kind of more simple liquid. And what that means is if we deform them, it means that the trajectories of the particles in this context depend on the strain that we apply and the history of the strain that we apply. So if you have water in a cup, the kind of average positions of the particles, of the molecules, doesn't really care if you're shearing them or not, because they're moving around so quickly. Whereas in this case, any diffusive time scale is either similar to the flowing time scale or the shearing time scale, or slower than it. So that means you can't describe the system without knowing about the deformation or the history of the deformation that's been applied. That makes it interesting and complicated. So it has some microstructure which evolves dependent on the strain that you have applied to it. It isn't true of something which is in equilibrium. Another complexity is that, like I said, when you have a mixture of roughly equal volumes of solid and liquid, we describe this as crowded conditions. So what that means is that the gaps between the particles are generally smaller than the size of the particles themselves. And that means the particles can come in and out of contact under small deformations. So if we apply a small amount of strain to a system, you can suddenly kind of cause particles to come into contact or interlock with each other. And that means that the stress can vary wildly under small deformations, depending on whether you're bringing particles into contact and what the properties of those contacts are. And that leads on to the third complexity, which is that we don't have a kind of toolbox of interaction models that describes how these roughly micron-sized particles should interact with each other. We know how atoms and molecules interact. We know how macroscopic macroscopic objects interact, but solid particles which are 1 micron in size sort of have elements of both. So these particles may have electrostatics being relevant as a repulsion. They might have van der Waals forces being relevant, but they might also have macroscopic concepts such as the Young's modulus or something like that to describe them more from a solid mechanics point of view. And that makes kind of understanding the particle-particle interactions kind of complicated. And generally you find that you have kind of tangential forces. So in the photo I showed you of the particles, you can see that they were angular. You can imagine that they would interlock or have some kind of resistance to rolling. So the interactions between them obviously have tangential components as well as normal ones, which again brings in some complexity that wouldn't be present in a molecular liquid. So this list isn't exhaustive, but it's a few interesting sources of complexity. So I just wanted to show this famous experiment, which is still, I mean, it's 40 years old, but it's still, in some sense, not resolved from a kind of constitutive modeling point of view. So let me talk you through what's happening here. So on the right-hand side is a Couette rheometer. So we have here an outer cylinder. So they're usually about this size. So you have an outer cylinder, which is held stationary. And sitting inside that is an inner cylinder, which has a smaller radius. And that's this white thing here. And then you rotate the inner one. And knowing the torque that you're applying to the inner cylinder and the rate of rotation of that inner cylinder, you can compute what's the viscosity of the material in between and what's the shear rate in the gap. So if we put in one of these dense suspensions, so this is a dense suspension of order micron or larger particles. There's no Brownian diffusion. The trajectories of the particles are just set by the straining that we're doing. So you stir the inner cylinder and it causes the liquid and particles to be dragged around. And what they've done in this experiment is they've rotated it in one direction, which we can think of as this first block here. So this is time along the x-axis. So from some starting time until some later time, they've been stirring it with a constant rate and measuring the torque. And you find that there's this transient in the torque where it initially jumps from 0 to some value, and then in a very short time, and then there's a slower evolution before it reaches a steady state. So what we think of as happening here is that the particles are initially kind of homogeneously dispersed within the suspension, but then as you start shearing them, they arrange into a shear-induced microstructure, which is different from the homogeneous one. So the particles preferentially take on certain positions relative to each other, and it takes some amount of straining before you achieve that, and that's why there's this slow transient. Then what happens if you stop the shearing? The stress immediately drops to 0. And then if you start the shearing in the opposite direction, you get the same thing, but it's now negative. So negative shear rate just means we're reversing the direction. So again, you see the torque is negative, but it does exactly the same thing. So it again, very rapidly takes on an intermediate value and then has a slow evolution towards a steady value. So that is to say that the microstructure has some kind of directionality. So we sheared it in one direction and it built up a microstructure. But then when we sheared it in the other direction, it had to kind of undo that and form a new one with alignment that was reversed with respect to the first one. And interestingly, if we then stop shearing again, stress goes to 0. And if we then continue shearing, this time not changing the direction, the stress just jumps, the torque jumps directly back to where it was. So the microstructure was preserved. After we stopped shearing, the particles just stopped moving. There wasn't any diffusion, which meant that the microstructure didn't change. So as soon as we started shearing again, everything just remained intact, and it kind of recovered the steady state stress from before. I think this experiment took a long time to be kind of digested by the community, but we still don't have, I mean, we have a lot of progress, but we don't really have a mathematical model that can describe this situation entirely satisfactorily. So there are efforts to do it, and they're relatively good at capturing the main features, but they don't capture the details. So there's a kind of challenge there. Okay, so in order to start to understand this problem, it's good to consider what are the parameters. So suppose we have some solid particles, this time they're spherical, of slightly different sizes in a fluid. So I've written down, I'm not sure whether this is exhaustive, this list, but I've written down a list of the particles, of the system properties that I think are relevant. So there's the size of the particles, there's some measure of the hardness of them, there's the density of the particles, and I'm taking that to be the same as the density of the liquid. So they don't sediment or they don't float under gravity. The liquid I'm assuming to be Newtonian, so its only property is its viscosity. And then I have some shear rate, which is tensorial, and a stress, which is tensorial, and the solids fraction, which, like I said before, is the fraction of the total volume taken up by solids, which is going to be roughly 50%. So if we construct from this list some timescales, there's 3, and I've written them in this way. Well, I'm not saying there are 3, but I've chosen 3 of them and written them in the following way. So there's a timescale associated with the duration that 2 particles will spend in contact with each other. So if 2 particles are pushed together by the liquid flow around them, they'll resist that. They'll want to push away because they're rigid solid objects. And the timescale associated with that will be something like this. So this thing has units of time. So if these are solid objects, and the Young's modulus, or the hardness, whatever we want to call it, will be a large number, which means that the timescale will be short. So that basically means if 2 particles are pushed into contact, that will relax almost instantaneously compared to anything else, any other processes happening in the system. Another timescale we can identify is this one, which is the density of the particles multiplied by the size of the particle squared, divided by the liquid viscosity. So this is this timescale kind of tells you if a particle has a velocity different to the fluid velocity at this position, how long does it take for the particle to dissipate enough energy that it's moving with the same velocity as the background fluid at that point. So you can think of this as the time scale for the particle inertia to be dissipated. And again, if the particles are going to be micron sized and they're going to be suspended in a viscous liquid, then a squared over each is going to be a small number. So again, we can treat that as 0, which basically means that the particles are always going to be moving at the same velocity as the fluid immediately around them. So what we're left with then is that as the time scale is just the inverse of the strain rate that we're applying. And that means if we want to come up with some dimensionless control parameters for understanding suspension flow, we can only have some things that look like these 3. So the solids fraction I mentioned is already dimensionless, so that just goes straight onto our list. There's only one relevant timescale, which is the shearing one. So the only way we can make this dimensionless is with the stress and the liquid viscosity. So we write this as a reduced stress. So this is the stress tensor, and it's rescaled with the liquid viscosity times the strain rate tensor. So this thing here has units of stress. So this is a dimensionless stress. And depending on our interests, we can, in principle, these don't have to be I and J, this can be I, J, and K, and L as well. So this is one of the relevant dimensionless groups. Then we have the stress tensor itself. Each of the components might have different dependence on the reduced stress on phi. So we can write down the ratio between any of the elements of the stress tensor as another control parameter. So in the steady state, so this is after, in this experiment I described before, the steady states are these ones, where we reach a plateau in the torque. In those steady states, the system is fully defined, knowing these 3 dimensionless groups. So there was a very well-cited paper which tested this, conducted by François Boyer, Elizabeth Gouzelli, and Olivier Poulecan, French group. And they built their own rheometer, which they could use to test this argument about the 3 dimensionless groups. And so this device has particles in here, which I think are hundreds of microns to millimeters in size. And they put the particles in a ring, and then they shear the top of the ring. So they're applying a shear flow. And the important thing is that there's a grid here which allows the fluid in and out, so the system can dilate or compress depending on the stress that you're applying, which means its volume fraction is allowed to change. And I'm not going to go into too much more detail about the experiment other than to show you the result in which they found indeed that because there are three dimensionless groups describing the system, you can write it down as two functions. So the ratio of the stress is a function only of this quantity here, which is the reduced stress that I mentioned before. And similarly, the volume fraction is only a function of that. So this was a really nice demonstration. Each of the different colors here are different sets of parameters, different sizes of particles, different shear rates, and so on. And they all collapse in this way, showing that the constitutive behavior of the material, or that the rheology in general is well described in using the quite simple arguments I made on the previous slide. So this is kind of now established as the rheology of a suspension of hard spheres in the way where the liquid is very viscous, the particles are very hard, and the inertia of the particles is not relevant. So I'm going to show you some simulations which we used to test the same idea, to both kind of test the arguments about the dimensionless control parameters for the system, but also to verify whether the simulation itself actually is a good representation of the experiment. So, I mean, people have different reasons for doing simulations. This is kind of more relevant to a chemical engineering audience, because I think chemical engineers look to use simulations to model processes and try to do more than they can do experimentally. But I think from a more fundamental point of view, there's some really interesting things which we can use simulation for. So I like to use simulation to test basic physics. So the thing that's great about it is you can construct a minimal model. So you can prescribe exactly the physics that you think are relevant, whether that's the drag forces on the particles, the particle-particle contacts, and so on. And if you don't like those physics, or you don't understand them, you can just switch them off and get rid of them altogether. So, for example, we've turned off the Brownian forces, so there's no diffusion whatsoever of the particles, which in reality is true if the particles are big, but generally there's a little bit of Brownian motion there. We also turn off gravity, so I said that we can assume that the density of the particles is the same as the density of the liquid. Obviously, in the experimental case, that's not really true, and particles will sediment. But in the simulation, if we don't want gravity, we just switch it off, and then it's not there. So we can really kind of take the complexity really down to a minimum, try to understand something, and then systematically add complexity back in to understand the role of different physics. Once we've done that, we can then kind of explore the parameter space. So actually doing these experiments that I showed is extremely time consuming, because you have to load up the particles into the rheometer, check the volume fraction, clean the device, unload it afterwards. And if you wanted to look at a very broad range of parameters, it would take weeks of experiments to do that. With a simulation, you can just write a code which just loops over a parameter and put it on a cluster and come back a week later and it's done. So you can really explore the parameter space much more quickly in terms of your own time, maybe not in terms of the computer's time. And finally, with a simulation, especially a particle-based simulation, we have access to all the details about the particle's trajectory. So we can know the position of every particle as a function of time, something which isn't available in the experiment. And we can use that detail to understand mechanisms, kind of find a resolution, and to construct constitutive models that are motivated by the microscopic details. So the simulation that I ran is the following. So it's extremely simple. So the particles, which are these gray circles, have an equation of motion, which basically says that their mass times their acceleration is some function of their velocity, some function of their position, and in general, the h of theta might be some Brownian noise or something like that, but I've switched that off so you can forget about the h of t. So these forces are kind of broken down into two sets. So there's hydrodynamic forces, which describe how the two particles would interact with each other through the liquid. And then there's contact forces, which describes how particles interact at contact. The hydrodynamic ones have two parts. So there's a Stokes drag. So this is, every particle has a a velocity, and the background fluid has a velocity at the position of that particle. So this is a drag force which pulls the particles along at the velocity of the liquid. Then we have pairwise lubrication forces. So this is a force that if two particles are moving together, you have to squeeze the liquid out of the gap. So there's some viscous resistance to moving particles together. Similarly, if you want to move particles away from each other, you have to draw liquid back into that gap. So then if particles moving away, then it becomes an attractive force. So these are very short range and pairwise hydrodynamics, which depend on the relative velocity of two particles, which is v2 minus v1. And finally, we have contact forces, which are very, very simple. So the contact force is just a stiffness of the particles, which is related to the Young's modulus G I mentioned before. This delta, which is amount of overlap of the surfaces, so it basically measures the deformation of particles at contact. And then a vector n, which is just the unit vector from center to center of the particles, telling you the direction. And we can have a tangential component of this contact force as well, but I don't really need to go into that too much just now. Okay, so once we've described these forces, we take our simulation box and we put it, we subject it to a shear flow. And the best way to think about that is that we put in imaginary replicants of the simulation box above and below, side to side, and in front and back. And we move the top layer of imaginary boxes in one direction and the bottom layer in another direction. And that produces this velocity profile, which I'm showing in orange in this middle box here, together with the Stokes drag, which helps to enforce that velocity profile. So we don't explicitly simulate all these duplicates, but we kind of have a trick to do that. So there's no solid boundaries here. We call it periodic boundaries, and we call this shearing a Lees-Edwards boundary condition. So that's how we apply a flow to our system. We specify the velocity at the top and bottom and force it to be linear by using the Stokes drag. Okay, so then we can, this is a snapshot of the simulation. It's not that, I mean, I tried to make it as pretty as possible by making it colorful, but just spheres in the box. So then we measure the stress, and the stresses just come directly from the forces. And so I measured exactly what was measured in the experiment. So on the top is the simulation result, and the bottom is the experiment. And you can see that the simulation does a pretty good job of predicting experimental behavior. So just to remind you, this is a non-dimensional stress. It's basically the shear rate divided by the normal stress, which is the stress on the top and bottom of the box. And then here we have the ratio between the shear and normal stresses. So these are both dimensionless quantities. And this one we have the dimensionless stress and the volume fraction. So qualitatively, you can see it's very similar to the experimental result on the bottom. The black lines in both of these are given by the same set of equations. I just had to change the limiting values as this number goes to 0 to make it match the simulation. So it's not a quantitative match, but it gets the general behavior very well. So there's a really crucial quantity here which describes the rheology, and that's this thing called phi m. So that's the maximum volume fraction that the system can flow at. You can see in the experiment it occurs at around about 0.58. So I said that we're mixing solids and liquids with roughly equal volume. It turns out the maximum that you can actually do that, in this case, is when the solids are 0.58. In the simulation, it's a little bit higher. It's 0.59 something, but it's pretty close. So just a couple of examples of some simulation results that add a little bit of complexity to this. So on the left-hand side here, the simulation I described on the previous slide was using a simple shear flow, which is this one. This is kind of a cartoon of what happens. So we distort the system like this. You can imagine other types of deformation where we squeeze the box in various directions. Both of these preserve the volume. So if you measure the relevant component of the stress against volume fraction in each of these cases, you find that they qualitatively the same, but the numbers are actually a little bit different. So it doesn't matter which one's which, really. The blue one is the shear, and the other colors are the various types of extensional flow. What's important, though, is that you find that the phi m, the limiting volume fraction, is very slightly different for each of these cases. On the other side here, we've got the same kind of simulation. This time we're doing simple shear, same as this, as a function of solids volume fraction, but we've varied the particle-particle interaction from a kind of smooth spheres which could slide past each other but not interpenetrate, up to kind of geared ones which could roll past each other but they couldn't slide, and finally to these kind of interlocked gears which couldn't roll or slide. So if these two particles come into contact, they have to move as a rigid object, as a pair. And as you add in these additional constraints on the pairwise motion, you find that the phi m, it's called phi j here, but it's the same thing, shifts to the left. So if you constrain the particles to move as rigid bodies when they come into contact, you drastically reduce the maximum solids fraction that you can achieve in the system. And these are very kind of broad principles that can apply. So this type of idea is relevant to like the kind of geophysical flows I mentioned at the start, as well as, in fact, in chocolate, there's a couple of papers that recently demonstrated that as they're making chocolate, as they're milling down the powder, they're actually shifting the system from this type of interaction to that one, which changes you can imagine if you're fixed at one volume fraction, but you change the particle interaction, you move your limiting phi m across, which means your viscosity drops. And that's a really important idea, which I'm going to go into a little bit more detail of. So, and this is where it kind of all comes together as how we can use this simple idea of suspensions just being controlled by the three parameters I mentioned before, and use that to address more complex examples where there's rate dependence. So the stresses depend on the shear rate, basically. So I presented here the same simulation data from before. I've just recast it in a slightly different way. So this time I'm plotting the suspension viscosity, which is the shear component of the stress divided by the shear component of the strain rate, as a function of the volume fraction. So you can see, this is just telling you, as you add solid particles, the viscosity increases and it diverges at some point that we call phi m. And the black line is a fit to some kind of expression like this. So we say that it diverges with an exponent which is close to -2. Depends who you ask and whose data you look at as to whether it is -2, but it's something like that. So the way that we can introduce rate dependence into this model is by saying, what if this phi m, this limiting solids fraction where the viscosity diverges, what if that quantity itself depends on the stress? Which would mean that this black curve might shift to the left or to the right, depending on the shear rate or the stress that we're applying to the system. And we can do that we can construct a mathematical form for that using quite simple, this is probably the simplest one you could do, in which you make the kind of active phi m be some linear interpolation between two values, so phi 1 and phi 2, let's say, and then have that interpolation happen as a function of the stress through some parameter like this. So this is just the stress relative to some stress scale. So what would happen in this system is that depending on which way around you specified this phi 1 and phi 2, if I've drawn it this way around. So if phi 1 is smaller than phi 2, that means that the jamming point, which is where the viscosity diverges, it will increase as we increase the stress in the system. So that means you have your viscosity function of the volume fraction set by this green line, but as you increase the stress, the green line will shift to the right until it lands on the purple line. So you can imagine if you're on a fixed volume fraction, for example, 55, percent here, and you're at low stress, then your viscosity is set by this green line. If you then increase the stress so that your phi1 switches to phi2, suddenly your viscosity is on this purple line, and it's dropped quite radically. So that means that your viscosity will drop as a function of stress, or we call that shear thinning, simply because the maximum solids fraction has shifted. So this idea is almost entirely attributed to this paper from 2013, where they did the reverse. Actually, they assumed that the maximum packing would decrease as you increase the stress, and then you get these interesting flow curves. So think of this as a stress as a function of strain rate. The flow curve has this S-shaped behavior, but actually, if you look hard enough in the literature, you can find a paper from a year earlier which incorporates most of the same ideas. So this is the type of rheology you get if you have a model where the maximum packing fraction phi m decreases as a function of the stress, and you can really get some quite complex behaviors. So in the next two slides, I'll just show some examples of how what kind of microscopic mechanisms might lead to such behavior. So suppose you have rough particles or angular particles or something like that, but they have a electrostatic repulsion or some kind of repulsive force which acts to keep their surfaces separated. So here's the angular particle, here's the repulsive force, which is increasing as the surface separation decreases. So we can set some kind of critical force scale where the particles get close enough that the interlocking can start to happen at the surfaces. So basically, if we apply a force smaller than F star, the particles don't know that they're rough because they're separated by this repulsion. But as soon as we exceed F star, the particles come into contact and they realize that they're rough and they start to interlock. So that's an example of a case where at low stress, the particles will remain kind of lubricated and they won't know about this interlocking. But at high stress, they will interlock. So that means that the maximum packing that can be achieved will decrease as a function of stress. Because as the stress goes up, they start to interlock and it becomes easier for the system to jam. So if phi m is shifting to the left, that means that the viscosity is going up. So we're forced to have a suspension viscosity, which increases as a function of stress. So that's what we call shear thickening. So on the other side, we can have some physics which cause phi m to increase as a function of stress. So an easy example of that is if the particles are adhesive or attractive. So shown in red is just a kind of adhesive interaction between these two particles. So they're stuck together, and then at some point they'll break apart. So at low stress, these particles will stick together thanks to some attractive potential or interaction, and at high stresses we pull them apart. So when they're stuck together, the system solidifies or jams because the adhesive contacts percolate the system, and everything blocks up. And that can happen at low volume fractions. As we increase the stress, we break these bonds, and then the particles just jam at the usual phi m, which will be higher. So that's an example of how the viscosity of the suspension would decrease with increasing stress. So this is the figure that we put in the review paper to try and describe this behavior. So you have, let's say you have a system which has a maximum volume fraction, which is where the viscosity diverges, which is a function of the stress. And then you have two stress scales, so sigma 1 and sigma 2. One of these stress scales might be causing the phi m to decrease with increasing stress. For example, the interlocking of asperities or the angular surfaces, whereas the other stress scale might be related to something which causes the maximum packing to increase with stress. For example, adhesive interactions or something like that. So the green and blue represent the two limits where you have one stress scale governing the system. So you'd either have shear thinning or shear thickening. And then the intermediate ones are for cases where both stress scales are relevant. So you might have some adhesion, but also some interlocking. And you can go back to the literature and find examples of rheology from experiments that fit into this picture in all three kind of categories. So here's a kind of typical shear thickening suspension, which maps back to the blue line, a shear thinning adhesive suspension, which maps back to the green one. And this is an example of the kind of intermediate lines where you have attractive interactions and shear thickening with slightly different stress scales, but both kind of observable within the same set of measurements. So this is an example where the maximum solids fraction is varying because of two stress scales, an attractive one and a kind of frictional roughness one. And then you get quite non-monotonic rheology. So the idea is to kind of come up with a set of principles encapsulated in this, which can describe a broad range of rheological observation. So finally, here's some open questions, which I just put brackets for applied mathematicians because I'm in an applied maths seminar. So you can easily add complexity to the things I've described, and suddenly the model breaks down very quickly. So, for example, this is work from one of my PhD students where he's mixing attractive colloidal particles with granular suspension particles. So the yellow ones are microns in size, and the blue ones are supposed to be tens or hundreds of nanometers in size. So how do you construct a model to describe a system which has two very different length scales of particles, as well as Brownian motion in the small ones, attraction in the small ones, but not in the big ones, and so on. So if we take two systems that are quite well understood, the blue particles, and another system which is quite well understood, the yellow ones, mix them together, it's not obvious how we should describe that. Once the particles become very non-spherical and have a high aspect ratio, again, we have an additional length scale in the system. It gets complicated. If we have everything I talked about was in a periodic domain, where we don't have any boundaries, we don't have any surfaces or interfaces. As soon as we introduce a surface, it gets complicated because you can see the roughness here. That's because the particles want to poke through the interface, and the capillary forces and surface tension resists that. So you get some balance between the stresses caused by the particles versus the surface tension and surface effects. There's really not much understood about that. And this one across the bottom is cases where the shear rate is spatially varying. So everything I showed you just had a linear velocity profile, which in experiments and the simulations, which means the shear rate is the same everywhere on average. But almost always in applications, and in the three applications I showed you at the start, the shear rate will be radically different depending on spatial position. So understanding spatial variance of the shear rate is crucial, but is at quite an early stage. So if there's any applied mathematicians out there looking for interesting problems, there's lots of problems. And I think that's all. So thanks a lot for your attention. Hope it's been interesting. I tried to keep it quite palatable, so tell me if I failed. Most of what I described is in this review paper. So, well, yeah, Tom can tell you whether or not that's easy to read or not. It's supposed to be for like graduate students, postdocs and stuff. So maybe you'll find it interesting. If you want to run any of these simulations, the code I used is LAMMPS, which is a very widespread molecular dynamics code. I added a few functions which aren't in the standard distribution, but you can download them there. And I have like a tutorial on Archive which describes how to do it. It's really easy to follow. And this is funded by the Royal Academy of Engineering and the Liberty Human Trust. So thanks a lot for your attention.
Excellent. Thanks for that awesome talk. Yeah, have we got any questions from the in-person or online audiences?
When you were describing the correct geometry at the start, you said that you rotated the inner cylinder, rotated, then you stopped and rotated again, and nothing happened. But what happens if you increase the time between the two rotations? What's the time taken for it to relax? How does that time give a time scales?
In this example, that is very slow. it depends on the diffusion time of the particles. So the only thing that would disrupt the microstructure is the diffusion, and I think the diffusion coefficient goes with particle size cubed or something like that. So for the particles of the size that were used in that experiment, you'd be waiting a very long time, not seconds or minutes. But if you repeated the same experiment with particles which were hundreds of nanometers or tens of nanometers, then the diffusion time would be very short, in which case it would go back to, it would homogenize immediately or very, very quickly after you stop shooting. So it really, you could almost measure the particle size using this experiment, because the time that you had to wait for it to redisperse would give an indication of the particle size.
I was wondering about polydispersity as well, as you mentioned a bit about biodispersity at the end. I mean, I think one of your renders early on with all the colourful particles that maybe looked like it had lots of different sizes. I mean, are you expecting, these ideas? You said you're not sure how a mixture of two different size classes are going to work. How about, the kind of smooth transition to polydispersity from monodispersity?
So I said that I was not going to worry about Brownian motion. That means I'm constrained to particles which are bigger than hundreds of nanometers, let's say, so micron size or thereabouts. And I also said I was not going to worry about particle inertia. So that means I'm constrained to particles less than tens to hundreds of microns. So really, I think everything I've said is applicable when the size of the particles is basically 1 to 10 microns. So any mixture of sizes, whatever the distribution, which is within that range, should be okay. As soon as we go broader than that, we need to add back in those extra physics of the Brownian motion, or at small length scales, at small particle sizes, or inertia at large particle sizes. And then those will just enter as, well, they can enter in one of two ways. So with the Brownian motion, coming back to this picture, when particles which are dominated by Brownian motion, if you put them in a high volume fraction, then they have a glass transition rather than a jamming transition. That is kind of governed by different things, but it's still a divergence of the viscosity with volume fraction. So for Brownian particles, the viscosity diverges at the glass transition, which is usually lower than phi m. So you might have a phi g, which is the glass transition volume fraction, which is low down here. Now, that would mean that as you increase the shear rate, the role of Brownian motion becomes less relevant. You move from the phi g to the phi m. So it's possible that the Brownian motion of the small particles could enter the same framework as a kind of phi m reducing physics, in the same way that attraction does. But the inertia, like we discussed earlier, I think doesn't fit that framework, because it's not obvious that the presence of inertia, which you would have if your size distribution included large particles, it's not obvious whether inertia affects phi m. So probably inertial particles wouldn't fit into the phi m changing physics model. Then you might need to do something else. So yeah, there's certain size ranges where I think you can use this, others where you might need to think about other things.
Yeah, well, if we don't have any more questions, we can thank Chris again, and
Thank you.
I think Chris will be available for maybe 5-10 minutes.
Yeah, I should apologise. I'm going to Durham in an hour, so I'll stick around for what looks like very unhealthy treats, and then I'll have to run off and do it. But thanks a lot for having me.